Hi everyone, my name is Tugu Santoso Lembono. I'm a PhD student at IDIAP Research Institute and EPFL, Switzerland. I'm going to present my work, learning how to walk while starting optimal control solver with memory of motion. So the objective of our work is to make legged robots walk optimally. So to do this, previously we have proposed Crocodile, an optimal control solver based on differential dynamic programming or DDP. And we have shown that this can work with various legged robots and to produce highly dynamic maneuvers. However, if we want to make this working in a real-time setting, we need to improve the performance even further. And one way to do this is to provide good initial guesses to the system. And this is the focus of our work today. So here we have an optimal control solver that we want to warm start, and we use memory of motion to do that. Basically, if we have learned how to walk before to certain goals, and then we are given a new goal, we should not relearn how to walk from scratch again, but instead we should use our previous experience or our memory to guide us towards this new goal, and that is what we propose. We use motion generation to generate a lot of data set of motion that we stored as memory of motion. And then if we are given a new goal, we can use this memory of motion to provide initial guess to the optimal control solver. And to generate the data set, we use HPP Loco3D, locomotion planning framework that is based on 4 stages. First, it plans for the route of the trajectory of the robot, and then it generates contact sequence, centroidal trajectory, and finally the whole body motion. This is the example of the motion generated by HPP. Here we have one-step dataset. We can also have multi-step dataset even while avoiding obstacles in the environment. In this work, we choose to focus on learning the one-step dataset, and we will use this later as a building block for multi-step motion. There is one problem, however, in this framework, because we use a different solver to build the dataset as compared to our online solver. So when we learn from this dataset to generate initial guess, the online solver will then need to spend additional iteration to refine this motion. So our proposal is to re-optimize the first dataset by Crocodile, so by the online solver, so that we can obtain a second dataset CRL that will be used as the memory of motion. We'll compare these two datasets later, and we'll show that by learning from the second dataset, it can give us better performance. This is the difference between the two datasets. Dataset HPP will tend to produce motion that are more conservative, whereas on the second dataset, we have motion that are more optimal according to the cost function that we provide to the Crocodile. Having the dataset, how can we learn how to produce good initial guess? First, we choose to represent the trajectory using dimensionality reduction techniques. So let's say we are given a trajectory y, which can be state or control trajectories. We use radial basis function to represent it as weights, so that the dimension is decreased from d by t to dk, where k is the number of basis functions. And then we reduce the dimension further using PCA. And now we formulate the problem of inferring the initial guess as a regression problem to find the mapping between x, the task, and y, the trajectory. And x here in this case is the desired contact location. To solve this problem, we use GMR and GPR, and we compare the performance of these two methods. So this is the warm start generated by the different methods. We can see generally that GPR can produce motions that track the desired contact location more accurately as compared to GMR, although GMR can still do a pretty good job as well. And as comparison, we include k nearest neighbor with k is equal to 1 to show what kind of motion that we actually have in the dataset. And this really shows that GPR and GMR really does interpolate well. Here we see the same thing, but by learning from the second dataset, CRL, and we see the same trend. GPR is more accurate than GMR. Then we use it to warm start Crocodile, and we compare against cold start, where we initialize Crocodile with the value 0 for both state and control trajectories. And generally we see that warm starting Crocodile gives us benefit in terms of a lower number of iterations. And then learning from the second data set gives us better improvement as compared to the first data set of HPP. Another thing interesting to note here is that while we have stated previously that GPR is more accurate than GMR, in terms of the warm starting performance, they are actually quite similar. So it means that more accurate function approximator does not necessarily mean better warm starting performance, because anyway the solver will still need to optimize the motion a little bit. Then we also compare the components used in the warm start. So we try to warm start using only the state trajectory or the control trajectory, or using both. And here U0 is not the predicted control trajectory, but it is computed based on Q and based on quasi-static assumption. Here we see that warm starting using both will result in the largest improvement in terms of the number of iteration. But if we don't predict the U, but we compute U based on Q, we still get very similar performance as well. Then we use the single step motion as building block for creating multi-step motion. So given a desired contact sequence, we use the single step motion at each of the contact sequence, so that we can have this motion. This is generated by GPR, and then we feed this into Crocodile, and then the motion is refined by Crocodile by several iterations. And finally, we compare the warm starting performance in multi-step motion. We use 3 as the number of steps here, and here we see that again warm starting using the second data set is better as compared to the first data set. But interestingly, the number of improvement is not as big as before, and the one by HPP is even worse than cold start. This is because the one-step motion that we use always start from 0 velocity and end at 0 velocity as well. So when we choose to use this for building multi-step motions, it is definitely not optimal, and Crocodile needs some time to refine this motion further. In summary, we have presented a framework for warm starting an optimal control solver for locomotion, and we show that the number of iterations is reduced significantly in the case of one-step motion, and we have compared the effect of different warm start components, whether we warm start using only the state or the control, or both trajectories. And some further challenges is we need to improve the performance on multi-step motions. We can do this by using the motion from multi-step datasets and divide this into single-step motions. Doing so will give us motions that start and end at 0 initial velocity. Or we can intentionally build a new dataset with one-step motion that starts from non-zero initial and end velocity. Then the optimal control formulation used in this work is also not very realistic, because we haven't considered torque limit, friction cone, and obstacle. We are doing works on this, and once these are included in the formulation, the optimal control problem will be more difficult, but it will give us more opportunity because warm starting this optimal control problem will give us more benefit as compared to this work. Thank you for attending this presentation. We encourage you to also look at our other presentation as well. Thank you.